In example 2, we're going to look at an example where we have an equation involving modulus, moduli of complex numbers, and we want to understand the solution set in a descriptive way. Descriptions can be a vague concept, namely, what do you mean to describe it? Do I write you an essay? Do I draw you a picture? Do I give you a solution set? And we're going to do all of those. Well, not the essay, but we're going to describe it in such a way that if we had to work with the numbers satisfying this, we would have a pretty good idea of how to play with them. So that'll become obvious when we do this problem. So we want to know the z's in C, so the complex numbers, that satisfy the modulus of z is the same as the modulus of z minus I. And before we get started, what we can do is try to get a handle on what either side of these means. So let me just go on a slight tangent here. When we write z minus a, where z and a are complex numbers, this is sort of the distance, well, it's not sort of, it is, the distance from a to z. Or it's not directed, let me just say between a and z. Straight line distance. So with that in mind, z we can think of as z minus 0. This is the distance between 0 and z. And z minus I we can think about as the distance between I and z. So in other words, what we're looking for is we're looking for the z's that have the same distance between 0 and I. So if you were to pick a z and you were to compute its distance to 0 and the distance to I, you would get the same number. So let's try to draw a picture, and then we'll go into the algebraic computation. So I'm going to mark 0 in the complex plane, and then I'm going to mark I. I is up there. So I want to make sure that my distance between 0 and I is the same. So one acceptable point is here in the middle at 1/2 I. 1/2 I has a distance of 1/2 to I and 1/2 to 0. A point which I'll put in red, which is not okay, is something like 1. So it's not a solution. Because the distance to 0 is 1, whereas the distance to I is clearly more than 1. In fact, this is not the correct spot. Let me put 1 in the correct spot. The distance to I is √2. So 1 would not be a solution. So what do we need to make sure? Well, if we go out a little bit, we want to make sure that our distance between I and 0 sort of remains fixed. And if you think way back to a course in Euclidean geometry, for example, the set of points that has the same distance between two given points is the perpendicular bisector of the segment joining those 2 points. So in other words, if in green I were to draw the segment joining 0 and I, the set of points modulus z minus I equals modulus z is just the perpendicular bisector of that segment. So this is z minus I. So there we have a geometric description of what the solution set is. And we're now going to go ahead and give an algebraic description, and we're going to see it agrees with our geometric description. But we should expect, after we're done, the equation of a line. In particular, this is the line y is always 1/2 I. So whatever we're about to do algebraically, we should arrive at that as our answer. So for the algebraic description, or even just an algebraic way of approaching this problem, I should say, I'm going to leave it as algebraic description though. We are going to take a random complex number x plus iy. And then we're going to look at the equation modulus z is modulus z minus I. So let's plug that in. So we have to do a preliminary computation on the right real quick. So let's do that. X plus iy minus I. The left-hand side we'll leave alone for a second. On the right-hand side, we can factor out an I. We'll get a y minus 1 when we factor out the I. So now we're in a position, to take the modulus of both sides of this. So the modulus is the square root of the real part squared plus the imaginary part squared. Don't put i's here. And the modulus of the right-hand side is x squared under the square root plus y minus 1 squared. Great. Now, the square root is kind of messing things up. So let's square both sides to get rid of that square root. So when we square it, the left-hand side will be x squared plus y squared, and the right-hand side will be x squared plus y minus 1 squared. And we could write that y minus 1 squared as y squared minus 2y plus 1. Now what do we notice here? We notice that on both sides of this equation, there's an x squared, so we can cancel, and there's a y squared, so we can cancel. We're left with 0 is negative 2y plus 1, and that is easy to solve for y. That's y is 1/2. And sorry, I'm realizing I made a slight notational error earlier, and that's okay. We make mistakes. It should be y is 1/2 up here. Now, of course, y is a real number. It can't be 1/2 I. So this is all points for y is 1/2. And that's what we got here for our solution as well. So we have our geometric description. We have our set theoretic, if you like, algebraic description. And then we can also even just say, just to be very clear, the solution set to z is the modulus of z is the modulus of z minus I is the horizontal line y equals 1/2.